Hello. In this lesson, we'll take a quick look at probability distributions. The term sounds probably intimidating. We are not trying to get into great depth about the theory of probability distributions and so on, but I just want you to have a very brief idea, the intuition for probability distributions. Okay, so obviously, whenever we talk about probability, almost the first thing that anybody talks about is a coin toss, right? We know that if there is a fair coin, we expect a roughly equal number of times heads and tails to come out. Okay, which is actually why coin tossing is used in games and so on to determine the order of play, etc. Okay, so we expect a 50-50 outcome, which means there are only two possible outcomes, heads and tails. And we know intuitively that the probability of a head is 0.5 and the probability of a tail is 0.5. Okay, of course this is only true if the coin is fair. If the coin is unfair and it's weighted heavily on one of the sides, then the probability of that side would become higher. But we are talking about a fair coin. Okay, so probability of head and tail are 0.5. Similarly, we can consider the roll of dice. That's another common thing that is used in examples of introducing probability. And of course we know that a common die has 6 sides and that all sides are equally probable, equally likely to come through. And again, that's why we use the dice in games. Okay, so a fair die, of course, we expect an equal occurrence, number of times occurrences of the die faces 1 to 6, which means there are only 6 outcomes possible, 1, 2, 3, 4, 5, 6, and the probability of 1 equals probability of 2 equals, etc., 1/6. Okay, so that's the idea of a discrete probability distribution. Okay, so when we say a probability distribution is discrete, that means the values that can result from it are discrete. Okay, which means if you have a coin, the values can only be head or tail. There's nothing in between. There's nothing out, on either side of head or tail. Okay. Similarly, when you have a die roll, the only possible outcomes are 1, 2, 3, 4, 5, 6. It's discrete outcomes. Okay. And often the number of outcomes is also finite. Often, doesn't always have to be. Often it's finite. On the other hand, continuous probability distributions can take on continuous values. Okay, so for example, suppose we take the height of people. Okay, now we may actually measure the height of people as 5 feet 1 inch, 2 inches, 3 inches, but actually speaking, a person is not either exactly 5 feet 1 inch or 2 inches. Okay, there's an infinite number of values of height, and any person can take on any one of these heights, right? If we measure with great precision the heights of people, then we will find far more values. Some people who are only like 0.001 inches taller than another person, etc. Okay. Similarly, weight and profit and sales and time, etc. Profit, you could say, well, because it's measured in currency and currency has only discrete values, you could say in a kind of sense that profit is discrete, any currency amount is discrete, but for practice we treat them as continuous. Okay. Similarly, anything with currency, of course, has the same point. Again, time is also continuous because you may say 1 second is the time interval, but again, you can have 1.5, 1.5, 0, 0, 0, 0, 0, 5, etc. It's practically continuous and infinite. Okay. Again, the time till the next customer arrives is a continuous value. A person can arrive at any instant. It doesn't have to be at the exact second or the exact minute. That's the difference between discrete and continuous probability distributions. In the case of discrete probability distributions, right, suppose I took a coin, which is a fair coin, and I tossed it 1,000 times. Okay, and I count the number of times I got heads and the number of times I got tails. Okay, we expect that the number of times we get heads and tails will be almost equal. Okay, in fact, it could turn out to be exactly equal as well, but that may not always happen. I toss it 1,000 times and I get 498 heads, and 502 tails. Okay, that could happen. Tails slightly more than heads. As long as they're almost equal, then you would say, yeah, it's possible the coin is fair, right? So that's the whole point. If the coin is fair and you toss it, you will get almost equal distributions of heads and tails. Similarly, if you take a look at dice and I throw dice 1,000 times, in theory we are supposed to get an equal number of occurrences of each die phase. Okay, of course that can never happen because 1,000 is not divisible by 6, so that's not going to happen. However, we'll get roughly the same number of values if we repeat the experiment many times. Okay, so that's another idea of probability distributions. Okay, so we can take any probability distribution, the theoretical distribution, and plot it. So for example, suppose we put head and tail on the x-axis here and we represent each with one bar, and we want to show the probability of head and probability of tail on a bar, then we'll show two bars, each of which have a height of 0.5. Right, that is, the probability is equal and half. Similarly, if we did that for dice, you would get 0.1666 or whatever is 1/6. Okay, so that's what you'll get for each one. Now let's consider another discrete distribution that we have been dealing with quite a bit in this course. Actually, we have our good old MPG data set, right? Now I can ask a question. Suppose I pick a car from this MPG data set at random. What is the probability that it belongs to a given class of vehicle? Okay, so now we can look at the distribution of the cars of different classes, right? So for example, you see here, these are two-seater cars, and on the y-axis, instead of putting the actual numbers for each of the classes, I have put down the proportion of the total that every class makes up. Okay, so given this, we could say, well, the probability that the car is compact is about 0.2. Okay, so that's, this bar is compact and its height is about 0.2, which is that 1/5 of the cars in the entire data set are compacts. So if I pick a car at random, then there is a 0.2 probability or a 20% probability that it's compact. Okay, similarly, the probability that the car I picked is a two-seater is only 0.02. That's the height of the bar approximately for two-seaters. Okay, so that's what we are seeing here. So in the case of discrete values, okay, the probability is simply the proportion that it makes up of the total, right? So heads and tails make up equal proportions, so the probability is 0.5 for head or tail. In a dice, you have the same thing. Whereas in the case of cars and the class from our MPG data set, okay, we see that the different classes of car occur with different frequency. There are different numbers within our data set. Okay, and if we look at the proportions of each of the cars, then we can say if I pick a car at random, then the probability that it belongs to a particular class is simply the proportion of times that particular class occurs. Okay, similarly, suppose I say I have a class in which the 70% of the students are girls and 30% of the students are boys, or women and men, and I pick out a student at random from the class. Okay, obviously there's a much higher probability that it's a woman because 70% of the class is made up of women. In fact, specifically, the probability that I pick a woman is 0.7, and the probability that I pick a male or man is 0.3. Okay, so in the case of discrete distributions, we generally just go by the proportions, and that gives us the probability. Okay, unfortunately, you cannot do the same thing for continuous values. Okay, so let's take a look at a continuous variable this time. This time we are looking at the distribution of heights of women in the US. Okay, now it so happens that we will talk about this later, that the average height of a woman in the US is 162 centimeters, and the standard deviation, right, because after all not everybody is the same height, there's variability, the standard deviation is 6.9 centimeters. Okay, now suppose we break up the heights of people into different intervals, right? So each bar here represents a certain interval of height. Okay, so this is 150, so you could say this bar represent represents 150 to about 152, right? So the number of people who have the height 150 to uh, 152, they are in this bar. So in our data set, it's about 40, 60 or so. Okay, that's the height, little more than 60. Okay, so what we have done here is we have created what is called as a histogram. And in a histogram, what we do is we take the continuous variable, divide the x-axis into intervals, and count how many values fall within a given interval. Okay, so here this bar consists of the interval 150 to 152. This bar consists of people who, the number of people who fall between 152 and 154 centimeters. And the height represents how many there are, right? So frequency is on the y-axis. So if you take any particular interval, every height represents a particular interval on the x-axis. You can just look up the y-axis value and see how many people fell into that range. Okay, so every bar really represents the number of people who fell into a given range. Okay, so that's one way of expressing continuous variables, somewhat like what we saw for the discrete variables. Okay, so once again here what we could do is to put probabilities, the proportions, take each bar and find out the proportion of the total it makes up and put that value on the y-axis. Okay, so now you can say what is the probability that somebody is between 150 and 152 centimeters? Well, I can look up the height of that. Okay, it's a little less than 0.04. Okay, so that way you can answer some questions about the probabilities in the case of continuous distributions, but only when you're talking about values falling within an interval. Okay, but of course we know that the number of possible values for a continuous distribution is infinite. Okay, so one thing we could do is, you remember we were doing the violin plot earlier, that gives an idea of the distribution. Okay, in this case we are talking about the inter-arrival times at a bank, meaning customers come to the bank and we are counting the amount of time that elapsed between one customer coming into the bank and the next customer coming into the bank. Okay, so let's say on average 12 customers land up per hour in the bank, or on average one customer comes up every 5 minutes. Okay, now this is a very common sort of distribution that is studied in statistics and in operations, and this is called as the exponential distribution. Okay, remember earlier we used the violin plot to study distributions, and we know exactly what it means. The violin plot is telling us if it's broad at a given point, it says that the density of points at that level is much higher than when it is narrow. Okay, so obviously we can say it's far more likely for a value to be here, around here, than for a value to be around here, because the width is so narrow. Okay, there's more of a crowding here, much less of a crowding there, and that's what distribution is really talking about. Okay, now another kind of distribution that is commonly studied is the normal distribution. Okay, and that is the example I showed earlier is also a normal distribution, the example of heights of women in the US. Okay, now the typical property of normal distribution is when you add many values which all belong to different distributions, then the net result is always normally distributed. And of course the normal distribution is commonly commonly identified by its typical bell shape. Okay, so here are many different normal distributions. Of course you're not seeing the bell shape because it's been turned, our violin plots are turned vertically, so you're really seeing various bell shapes like here standing on their side. And of course it's doubled because it's a violin plot. Okay, but that's the idea here. Normal distributions have a bell shape. Okay, so let's interpret some distributions. How do we interpret a discrete distribution versus a continuous distribution? Okay, so here the first one, of course, is a discrete distribution. We've already seen it is of cars, and we can take the height of a particular bar and look at the proportion of cases that that particular bar represents and say that is the probability. Okay, here's a discrete distribution which talks about the number of minutes between successive arrivals of customers, which I said earlier. One customer arrives, the next customer arrives. How much time did it take between the two customers arriving? It is quite possible that one customer arrives and right behind that customer, within 10 seconds, another customer may arrive. Or alternately, it could happen that one customer arrives and it takes 15 minutes for the next customer to arrive. Okay, so these timings, like 10 seconds and 15 minutes and 5 minutes and so on, that is called as the inter-arrival time in this scenario. Okay, it's very commonly studied in business situations, banks and railway stations and airports, and generally studied in the field of queuing theory. Okay, so what this distribution is showing you is that you see a big peak around 5. Okay, on average, it takes about 5 minutes between customers to arrive. Okay, but that's only an average. You could have customers arriving practically simultaneously, which is when the inter-arrival time is close to 0, and you could also have long waits, like it takes an hour before the one customer comes and the next customer comes, right? So inter-arrival times are continuously distributed, and they could happen, it could be 0 or it could be infinite. Okay, technically infinite. Somebody comes into the bank today and for the next 25 years nobody comes into the bank. Unlikely, but it's possible. Okay, so what we have done here is we have stood up the violin plot on its side, made it sort of be horizontal, and we've taken out, the violin plot is a symmetric thing with both sides showing the same thing. We cut out one half of it, and that is what this plot is, and this is typically how probability distributions are shown. Okay, now infinite number of values are possible in a continuous distribution. Like I gave the example earlier of people's heights. Well, there's actually speaking an infinite number of possible values for height if we consider, fractional values between 2 consecutive inches or between tenths of an inch, and even within that, right? So my height could take on literally any value within a reasonable range. Of course, no human being probably has ever been more than 12 feet tall, and no human being, probably an adult, has ever been shorter than like 2 feet, right? But technically even that is possible. Okay, but between the common ranges, any infinite number of values are possible, right? So whereas in the case of a discrete distribution, you could simply look at the bar and look at its frequency and say that is not its proportion of frequency, and say that is the probability. In the case of a continuous distribution, you cannot say that. You cannot say the probability that a customer will arrive exactly 5 minutes after another customer arrives. Okay, in other words, the probability that the inter-arrival time is exactly 5 minutes, that probability is actually 0. Okay, in a continuous distribution, the probability that the value is exactly equal to a particular value is 0 because the denominator is infinite. You have an infinite number of possible values, and you're talking about one among the infinity of possible values. Okay, so therefore that probability is 0 in a continuous distribution, and that's what makes a big difference between discrete and continuous distributions. Okay, so whereas in the case of discrete distributions, we can get the exact probability for a given value. So we can say the probability that a given car is a compact car is 0.2. Okay, we can say that precisely. In the continuous case, we cannot say that. In fact, we can say it precisely, it is 0. Okay, so the probability that the next customer will arrive exactly 5 minutes after this current customer has arrived, or exactly any number of minutes, 10 minutes, 12 minutes, 13.5 minutes, any specific value has a probability of 0 because there is an infinite number of possible values. Okay, so a continuous probability distribution is expressed in the form of what is called as a probability density function. Of course, it's a continuous curve, unlike a bar chart that we saw earlier. This is a continuous curve. Okay, and this happens to be the distribution of the heights of US women, where the mean is, on average, the height is 162 centimeters, and the standard deviation of the heights is 6.9 centimeters. Okay, and this is what the distribution is. Okay, now I cannot say what is the probability, or if you take a particular person, okay, the point is the height now does not give the actual probability, whereas in the discrete case the height of the bar gave us the actual probability. In the continuous case, the height does not give us the actual probability. So take, for example, a height of 162. Okay, now that cuts the y-axis at 0.58. Okay, it should be 0.058, I suppose. Okay, it's not 0.58, it should be 0. Because this is 0.06, this should be 0.058, not 58. Okay, but this does not mean that the probability of a randomly chosen US woman is 162. That probability is not 0.058, as we've already discussed. That probability is actually 0. Okay, in other words, in a continuous probability distribution, the probability that that particular variable takes on a specific exact value, that probability is 0. Okay, you can talk about that probability, but it makes no sense to talk about the probability because the value is actually. Okay, so in this slide we see a probability distribution. It's a normal distribution. This time the mean is minus 0.6. Okay, and a normal distribution, as I've already said, is bell shaped. Okay, and the peak of the bell will occur at the mean. Okay, so if you look at the peak and drop a line all the way down, you'll see that it meets the x-axis at the mean. Okay, so if you take many values and compute the average, you'll get something close to minus 0.6. So that's the average, and the standard deviation tells you how spread the values are. In this case, the standard deviation is 0.2, which is pretty small, and so the values are all crowded within a small range, and there are not too many values out far away from the mean. Okay, whereas if your standard deviation was larger, like in this case, let's say the standard deviation was 1, okay, then you'll have many values which are sitting far away from the mean. Okay, and the curve, the bell would be much flatter. In this case, you see a tall bell. In the other case, you will see a shortish kind of a bell. Okay, now of course, one thing you're seeing here is that the y-axis is going all the way up to 2. Okay, clearly that is meaningless, because meaningless in the sense that clearly that cannot represent a probability, right? Because a probability can never be greater than 1. So clearly the y values here don't represent probabilities, right? Now if you take the y value for x equals minus 0.75, okay, so that is somewhere here. Okay, its function value is 1.5, somewhere here. Okay, so obviously that also is not a probability. So one thing is very clear, that the probability density function of a continuous distribution, the y-axis values are not probabilities. Okay, now those y-axis values are what we call as relative probabilities. Okay, so the function value is a relative probability, and it makes sense only when seen in connection with other function values. Okay, so for example, the y value for x equals minus 0.25 is 0.43. Okay, what that says is that a value of minus 0.75, okay, is almost 4 times more likely than a value of minus 0.25. Okay, so minus 0.25 is somewhere here, so its height is coming somewhere here at 0.43, whereas minus 0.75 is here, its value is coming there. Okay, so you can now say that because the function value here is 1.5 and the function value here is 0.43, you can say that this is almost 3 point x times more likely than this. Okay, meaning given a distribution like this, there is a much greater chance that we will see a value of minus 0.75 rather than a value of minus 0.25. Okay, of course that is meaningful, right? Because this is a bell-shaped distribution and a lot of the probability points are concentrated near the mean in this particular case, and minus 0.75 is much closer to the mean of minus 0.6. Therefore, a value close to minus 0.75 is a lot more likely than a value which is further away from the mean at minus 0.25. Okay, so the height tells us the relative probability of any given value. Okay, so the height by itself doesn't convey much information. The value of it comes when you compare the heights at two different points. Then you can say this is more likely than that. Okay, so alternately we can say that an outcome of minus 0.25 is only about a fourth as likely as an outcome of minus 0.75. Okay, so here we are looking at again adult female heights. We know the mean is, this time I'm expressing the mean and standard deviation in inches. The mean is 63.5 inches and the standard deviation is 2.5 inches. Okay, and here we are looking at a height of 63, which is the somewhat below the mean. Okay, and we are seeing that that is 0.16 is the function value of that. Okay, of course that doesn't mean that the probability that a given randomly chosen person's height would be 63 inches is 0.16. No, that's not true. The randomly probability that a randomly chosen person's height is 63 inches is 0. Any particular value is 0, right? So here we are only talking about the function value. It's 0.16, and if you take a person whose height is 66, okay, their function value is 0.1. Okay, much lower. So that means the probability that you will see a person whose height is 63 inches is about 60% higher than seeing a person whose height is 5 feet 6 inches. Because this is 0.1, that is 0.16, it's higher by about 60%. Okay, clearly we know why that is the case again, right? Because we know the average is 5 feet 3.5 inches. So it's very likely in this particular case, normal distribution, it's definitely far more likely that you will see a person whose height is close to that than someone whose height is almost more than one standard deviation away from that, right? 2.5 is the standard deviation. So we are saying 5 feet 3.5 and and it's 6, right? So 2.5, one standard deviation away actually. Okay, so again, what makes sense is the relative heights, relative function values rather than the absolute function values. Okay, so we say a height of 5 feet 3 inches is 60% more likely than a height of 5 feet 6 inches. And again, now we are seeing a function value for 72 inches, okay, which is 6 feet tall, is only 0.0005. Okay, it's very small, right? It's extremely unlikely that you would see a person who's an American woman who's 6 feet tall. You will see them, of course. I'm not saying you will never see them. But compared to normal people, you will not see them that often. Okay, so a height of 5 feet 3 inches, close to the average, is 320 times more likely than a height of 6 feet. Okay, so you will see a tall person, a 5 feet 3 person, 320 times more often than you will see a 6 foot tall woman. That's what the distribution says, and that's what you can get from the distribution and the height of the function. Okay, so once again I emphasize the heights of a probability density function don't give you the probabilities, they only give you the relative probabilities. Okay, in fact, calling it a probability itself is dubious, right? Because it's not a probability, its values are greater than 1 and so on. But you can talk of it as relative, something that is 10 times more likely, but it still could be less than 1. Okay, so think of the function value at any given x value as the relative density of y values around that value. Okay. Now, one important point is in any probability density function, the area around the curve is always 1. Okay, that's the total probability. That area is always 1, and the shape merely tells us how that one unit of area is distributed across the range of the values. Okay, it could be uniformly distributed, or it could be peaked in one place, or it could be peaked in two places. It could be a curve where the more values are on the lower end, or more values are on the upper end, etc., etc. That's a distribution, but the total area is always 1. Okay. Now again, therefore, to find for in this particular case, to find uh, what is the probability that a person falls within a certain height range, okay, then all you have to do is to compute the area under the curve for that range, and you will get the probability. Okay, so here are some examples of many normal distributions with various means and standard deviations. Okay, so here you're seeing a normal distribution where the mean is 1 and the standard deviation is 0.2. Okay, so the standard deviation is really small compared to the mean, which means the values are not at all widely spread across. So you can see all the values are concentrated. This is a sharp peaked normal distribution where the values are all concentrated very close to the mean, because the standard deviation is very low, or in other words, variation among the values is very low. Most of them are closely distributed here. Okay, on the other extreme you see a distribution here. This is also a normal distribution. Okay, and its standard deviation is very high. Okay, its mean is also close to 1. Okay, but its standard deviation is relatively large. So you see that it's not as tall, and it's very wide. The values are widely distributed. Okay, whereas in the previous case there were very few values falling far from the mean. Here there are quite a few values which fall far from the mean. Okay, again here you see something that's in between. It's not as distributed as this, but again this is not as sharp as that. Okay, and then here you see one more, which is a kind of a tall one, but not as tall, right? Its mean is 2, the standard deviation is 0.4, more standard deviation than this one. So you can see that again the height goes down. Okay, now the important thing you have to understand is the area under the curve for each of these curves, that area is the same. Okay, so here all the values, most of the area is concentrated near the middle. Here the area is well dispersed out. Here also it's dispersed. Here it's still concentrated but not as much as this, etc. Okay, so the normal distribution is a very commonly studied distribution because it tends to crop up in nature all the time. Okay, so now there are other distributions which we won't really talk about very much, but these distributions play a very important role in statistics, and this is called as the chi-square distribution. Okay, whereas the normal distribution is described by two parameters, the mean and the standard deviation. Okay, the chi-square distribution has only one parameter. It's called the degrees of freedom. Okay, and we won't get into that concept of degrees of freedom, but just be aware that if you pursue studies in statistics, you will end up talking about the chi-square distribution. There's another distribution called the t distribution, which sort of looks like the normal distribution. Okay, but it's different. Okay, the t distribution you are seeing here with many different parameters. It's generally somewhat of a taller distribution than the normal distribution. Okay, very closely related, and there are many situations in statistics where you will find that normal distribution is not applicable because your sample size is not large enough. Then the t distribution becomes appropriate. So it's another very important distribution in statistics. Okay, so as far as this course is concerned, you really need to understand the idea of a probability distribution. Okay, the idea of the difference between discrete and continuous probability distributions, and the idea that in a continuous probability distribution, the density function doesn't actually give us the height of the density function doesn't give us the probability exactly. It only gives us a relative probability. When we do want to find probabilities in continuous distributions, we usually find the probability that a value falls within a particular range. We take the area under the curve for that range, and that becomes the probability.